Test, test. All right, we're going to go ahead and start our last block of sessions. For folks who may not have seen, I will just want to share a few reminders. One is if you have a green lanyard, which I see some of you do, make sure you return the lanyard to security on your way out. You will exit through 14. Tomorrow, I hope many of you, if not all of you, will be coming back to join us again through MPK 14. You'll go through the same security process, wear your badge tomorrow, and they'll just put a new sticker on it. Finally, we are hosting our conference reception at the end of this block of sessions, and we hope you all stay and enjoy some drinks and snacks and good times with the Velox crew. Okay, so with that, I am going to introduce James from Meta, who is going to be talking about GeoVelox.
That's it. Hello. Hi, I'm James Gill. I'm a software engineer here at Meta, and today I'm going to talk to you about one of my favorite subjects in the world, geospatial queries. Now, if you don't know anything about them, that's totally fine. I'll explain them. Almost nobody does. So the first question I'm going to answer is, what are geospatial queries? Because most people, like I said, aren't very familiar with them. And the second question is, why would we bother bringing them to Velox? It was a lot of work. There had to be a reason. And then lastly, I'll sort of tell you how to do it. Now, throughout this, I'm going to keep it pretty high level. Geospatial can get into the weeds pretty fast, and I want to keep you awake. But I do love talking about this stuff, so if you find me later, I can talk as many hours as you want me to talk about it. But for this part, I'm going to be more focused on concepts and obstacles rather than the nitty-gritty. So what are geospatial queries? Well, to back up a bit, I joined Facebook's connectivity initiative about 10 years ago. Not quite 10, but getting pretty close. And our mission was to connect another billion people. Now, this required us to find villages that didn't have access to power and build power lines to them, to find optimal paths of fiber optic cable backbone and lay them down in Nigeria and other places, and to reduce the per-person cost of cell towers and cell service so that it was more economically viable for cell companies to expand their coverage. But to do all this, we had to answer questions like, what towns are within 5 miles of a cell tower? What houses are in the overlap of 2 or more cell towers? What villages are not within a mile of an electrical line? And many, many more. These are all queries about locations and their relationships. And queries about locations and relationships, those are geospatial queries. Now, at first, Presto did not have any geospatial capabilities. We just ran our models on our local machines, maybe a machine in the cloud, but single machines. And that meant that we couldn't solve big problems. We could only solve small problems and small little parts of problems. But in 2017, Masha, who talked earlier today, added geospatial queries to Presto. And this was a game changer to us. Like computations that we just could not do before were done in minutes. Previously intractable problems suddenly became tractable. So we use this in a variety of ways, and one of which was we produced a suite of high-quality data sets that we opened up to the world. One, which I was near and dear to my heart because I was doing it for many years, is population density, which is the highest resolution and most accurate population maps in the world. At least it was a few years ago. I haven't done it for a few years, so who knows what's happened since then. Project North Star, where we added just thousands of miles of roads to OpenStreetMaps, and OpenStreetMaps is the open source alternative to Google Maps. Another thing we did was relative wealth index to understand which communities had the greatest need. We had many, many more of these. And these are all queries about locations and their relationships. So let's dive for a second into population density. Population is often measured in census tracts, which are kind of big polygons with a number of people that live in there. Now, if you don't know anything more, you kind of have to spread the people homogeneously across the polygons. You can see it's pretty chunky. It's very coarse-grained. But using some AI and some geospatial queries, we could redistribute this to like a 50-meter by 50-meter grid, right? Which just changed the game as to figuring out where people were and whenever we needed to figure this out. So, sorry, I talked a little too fast. I should let the reel play all the way. Sweet. Okay. But these are more than just numbers. So in this conference, you'll hear a lot of numbers, right? You'll hear about a CPU efficiency or latency gains or numbers of machines. But speed matters, and it matters in a lot of other contexts. It can make the impossible possible. So I'm going to talk about some other numbers here. So in 2017, El Nino caused flooding in Peru, and this destroyed 115,000 homes, left 178,000 plus some people homeless. In 2018, a magnitude 7.5 earthquake hit Papua New Guinea, leaving many people not only displaced, but also without access to food. And also in 2017, Hurricane Maria hit much of the Caribbean, but also Puerto Rico, where it not only killed about 3,000 people, but it basically wiped out the entire electrical and communication infrastructure of Puerto Rico, leaving 3.5 million people without power. So in all these cases and more, we partnered with governments and relief agencies, health agencies, the Red Cross, World Food Program, using our data and our computational capabilities to help them distribute relief aid to find people in need. So I remember after the Peru floods, I worked kind of late in the night because the World Food Program needed a map of where people were, and I could do that quickly, right? And I couldn't have done that quickly 6 months before. This is all because of geospatial queries in Presto. So when Maria hit Puerto Rico, it just, as I said, it wiped out the infrastructure. Now, one of the problems is if you lose access to the phone, how do you tell people that you don't have access to the phone, right? And so while electricity and connectivity was established in some of the major population centers relatively quickly, a lot of the more remote communities didn't have that connectivity reestablished. So we were able to figure out where Facebook activity had dropped dramatically between pre-Maria and post-Maria and help people figure out which communities they needed to go to reestablish infrastructure. And so you can see the graph here that a couple weeks after Maria, there was still a lot of loss of connectivity and communications, and this steadily got better. And the graph would get better and better over time. So it wasn't a nice to have, right? This is what allowed us to get the help necessary in time. So like I said, there's a lot of numbers in this conference. You'll hear a lot about numbers, but these are the ones that I care most about. So I hope I convinced you that geospatial queries are useful. Now the next question is, why spend the effort to bring them to Velox? Well, as we migrated from the Presto Java stack to the C++ Velox stack, we had a problem that I think many people in the room that have tried this have also encountered. When you have two stacks, you got a lot of problems. One problem is just increased cost, right? We had multiple clusters in each region, and some of these clusters were kind of underutilized. The clusters had like heterogeneous machine types, so all of that was kind of a really pain. Maintenance burden was real because each of the Java stack and the C++ stack had different failure modes. They had different semantics, so the operational burden was significantly higher. Dev velocity, of course, was reduced because you had to implement everything twice, and you couldn't even implement it identically, again, because there were sort of semantic differences. So the cost was real. But one of the biggest capability gaps was geospatial. Like I said, we had it in Presto Java, and we had it for several years, but we hadn't yet done that in Velox. And one of the first discussions is, should we even bring it over, right? And basically the answer is yes, we have to. We had a lot of internal and external requirements for that. Like internally, if you're a restaurant and you want to serve an ad to someone, you don't want to serve it across the country, right? You want to serve it in the town that you're located. The Ray-Ban Meta glasses need sort of contextual awareness of where you are. In Facebook Marketplace, you want to see items that are listed near you. You don't want to buy an item that's, again, thousands of miles away. And as I said before, data for good, there's all these maps that were all maps and other data sets that were very spatially located. But externally, there was a lot of demand too. IBM was one of their high-value customers. The migration was blocked because they required geospatial capabilities. Uber, as is pretty obvious, uses a lot of geospatial queries. But in general, the open source community had been asking for this since 2023 or so. But this leads us to the next problem, which is geospatial is very tricksy. It's a real pain. Anybody who's worked in it will sympathize with me. It's just kind of a different beast. There's many things that are different, one of which is a lot of properties that you take for granted don't really apply. Like you can't really hash geometries. In fact, you don't even have a good notion of equality, and we'll get into that later, but a lot of things you assume should work just like won't work with geospatial. A lot of the operations are extremely expensive and require a lot of deep domain knowledge to do appropriately. There's complex and non-intuitive standards. There's non-semantic but syntactical differences. There's numerical stability, and like a lot of these algorithms, you have to like modify the vertices of a polygon to fit a grid to deal with the numerical stability. So you have something that's not actually the same polygon, but kind of philosophically is. Edge cases are frankly kind of the norm, not super rare. So this also required kind of significant upfront development, right? If you had 90 functions, you might think, oh, we'll just throw 30 engineers for a couple weeks, and each engineer will do 3 functions, and we're done. But the problem is there's a lot of this like foundational technology that has to be done before any of those will work. And so a lot of the parts just were not parallelizable, and again, required a lot of domain expertise. So we actually had to start a full year before, and even so, we, we got pretty close to almost not making it. But there are many parts like the serialization and the types and the joins, which are just kind of single-threaded endeavors. So that's why we had to bring it and some of the initial problems. But I want to talk to you about how we brought Geospatial to Velox. And I'm going to focus on 3 core concepts and 3 obstacles. Again, I'm going to keep this high level because we're just not going to have time to go into the weeds. But I would love to talk about the weeds if you want to talk about it afterwards from 4 to 7, possibly with wine. Key concept number 1, the data model. The standards specify 7 geometry types. The first is a point, and that's the easiest. It's just a location, kind of X and Y. A multi-point is not much harder. It's many points. A line string is a sequence of locations in which you're sort of mentally drawing a straight line between each location. So it's kind of a piecewise linear curve. A multi-line string, no prizes for guessing this, is many line strings. A polygon has a closed line string as kind of a shell, and it may or may not have some interior closed line strings that represent kind of holes inside the polygon. Multi-polygons are many polygons. And lastly, and most problematically, is a geometry collection, which can contain any number of all the things we've described, including geometry collections. Now, why is this a problem? This seems like nice and well-defined, and it is well-defined, sort of. But some of the things it is just missing. So geometries don't support any sorting. There's no way to say one is greater or lesser than the other. They don't support hashing. They don't even support equality. While you might think that there's some topological point set notion, like, oh, if these contain the same points, in practice, calculating that is this very expensive operation that will give false positives and false negatives. There are many reasons for this, but one of the simplest reasons for this is different representations of the exact same geometry. So we see up here a square, pretty simple square, right? One of the simplest polygons you can imagine. And it has 4 corners, but you could express this a couple ways. One way is you start in the lower left at 0, 0, and you go to the right to 1, 0, up, left, down. But just as reasonably, you could start in the lower right at 1, 0 and go up, left, down, and right. Those are the same polygons conceptually, but they're not bitwise the same, right? So if you're going to check for equality, you can't just like check if the bits are the same. And this is as simple a case as you're going to get. When you have the polygon of Siberia, which is several hundred megabytes, that gets very hard. The next thing, which again seems like it's not going to be too bad until it gets bad, is geometry UDFs. Now, if you have 2 geometries, you might want to see what is their intersection or what is their union. How far apart are they? What's their distance? What's the area of one, or the length, or the centroid, and many, many more. The problem is that the implementation of these are very complex. Numerical stability is just a constant concern. You have to constantly make choices that are not actually totally semantically kosher, but are required to actually calculate things. The actual output in many cases is underspecified, and there are just many, many edge cases. Now, we get around this by using battle-tested open source libraries. Anyone who wants to make a geometry library, it's fun for the first 3 weeks, and then the next 10 years, you're chasing down edge cases and bug reports, right? So for the most part, if anybody wants to hire me to do that, I'm pretty excited to do that, but you won't get your money's worth. But there are ones that have been around for decades, and they've dealt with all this. In Java, in Presto Java, we use 2, JTS, or Java Topology Suite, and Esri is a very major GIS company, and they have an open source library in Java. And we use both of them for Presto Java. And if you really zoom out, basically what happens is you have a geometry encoded in some way as a var binary. You deserialize it. You throw it into the library. You take what comes out. Maybe it's a double because it's an area, or maybe it's another geometry because it's the intersection or something. And then you reserialize it, and you're done. So that should be easy, right? Well, there's a lot of little details, but there's a bigger problem in migration, which is there's actually no straight compatibility. Like, there's no perfectly compatible libraries for these. Now, JTS is the happy path. There's a library called Geos in C++, and It's nominally a port of JTS. The two maintainers are friends. They sort of, like if something happens in JTS, then the Geos people do it. I've worked with them for a while. They're great people, but there's just some differences between them. Just partly C++ versus Java, but also partly because, again, the standards are underspecified, so you have a lot of equivalent representations that come out of these things. Or you have things that differ by float precision or other numerical stability things. So while the general strategy for JTS was just find the equivalent geos function, sometimes that was like 3 weeks of work. But the Esri case was worse, is because Esri is a for-profit company that sells its GIS capabilities, and while the Java part is open source, the C++ source is how they make money, so they don't make that open source, so we can't just replace that. So we actually had to find geos capabilities that were as close as possible to the Esri ones. And again, sometimes that was pretty easy, and sometimes that was not. Now, the last major concept we're going to talk about is spatial joins. And now this is something I would love to talk to you about for an hour. I have about 5 more minutes, maybe 7 minutes, so I won't talk about them in detail. But if geospatial query is about locations and relationships, well, in general, joins are about relationships of the left side with the right side, right? And spatial joins are joins where the left and right side are both geometries. So examples are which roads intersect which cities, which points are contained within which polygons, which cell towers are within 10 kilometers of villages. And when most people think about joins, they think about hashable equijoins. They think about, oh, I have like t1.a equals t2.b, so I can hash them and I can distribute them and then I can do some hash table. But you don't have hashing and you don't even have equality, right? So how do you do this? You can always fall back to nested loop joins. And that is the default, but you know, nested loop joins are not always the most efficient. So let's take a step back for a second. Joins kind of do 2 main things, right? The first thing is for a given worker, they try to find the left side rows and the right side rows that match each other or match the predicate filter as quickly as possible. And the second is, when you have many machines, they try to make sure that any time a left side and a right side row would match, they're on the same machine. If they're on different machines, that's not very helpful, right? The machines don't talk to each other. They'll never know that they're matched. So these are these 2 key stages of joining, which is distributing them and then executing efficiently on a single worker. Now, in the single worker case, for a hash join, you just make a hash table, right? And you hash the join key on the left side, and you look in the hash table, and you get some right side rows, and maybe you have a more complicated predicate that you evaluate, or whatever have you. And you can't do that in spatial joins. The one answer, and probably the most popular answer that we use, is something called an R tree. Now, if you don't know what an R tree is, it's a fun and amazing world. It's a data structure where, like, every year a new academic paper comes out about a new, better R tree. But the concept is very simple, which is if you start with your geometries, you draw a box around them. And if you have 2 geometries, if they intersect, then their boxes have to intersect. So if you start with geometries and boxes around them, you make a group of them, and you make a box that contains all of them. And then you make a group of those boxes and make a box around those. And you go all the way up. So you have hierarchically nested boxes until you have this one box that encloses them all. So if you have a probe side row, a probe side geometry, you grab its box and you try to intersect it with the big root box, and like that's actually just 4 float computations. That's very easy. And if it doesn't, if the top level box doesn't intersect your geometries box, then you're done. Nothing's going to intersect, right? But if it does, you recurse 1 layer down to the children. You check each child box, and each one of those that matches, you check those children boxes. You go all the way down to find the leaf geometries that might possibly match a row. So easier said than done, but that's the way you do it. But we haven't really talked about distributed joins at all. And the spoiler is, well, I won't spoil it. So you also can't distribute via hash the way you can in a hash join. And so one way you can generally distribute things, if you have the right, if it's inner or not too bad for outers, is you broadcast. And this is something that we've talked about a bunch. It's relatively conceptually easy. Each worker gets the entire build side. So if there's a probe side and a build side row, or a left side and a right side row that match, well, if every worker has every right side row, then that match is going to be on that worker. So you sort of trivially get the property you want. It's not super efficient because each worker has the entirety of the build side, and you can run into memory pressures pretty fast. The other way is you want to partition it. But geometries have a really annoying property that's not unlike vector search and a couple other things, which is given geometry, if it's a polygon, any way you partition the world or the set, that polygon might be in multiple partitions, right? So generically, any build side or probe side row, for any partition strategy, will be in multiple workers. So now you have multiple workers. You have to dedupe any matches. If you have an outer join, just because you didn't match that worker, there might be another worker that matched, so you don't actually know if you can emit null or not. It's a real pain. Presto Java actually has partition joins, spatial joins, but they were always awkward because the shuffles are streaming in Presto, so you can't calculate statistics. If you have materialized shuffles, you can like pause for a second, calculate statistics, distribute stuff, and do it. So we had this kind of awkward but very useful partition joins in Presto Java. And we decided for round one to just skip it. The broadcast join was good enough for most of our use cases. We could fall back in other cases that were not super optimal, but were reasonable. And my personal hope is, because things like geospatial joins and also vector joins need this multi-partition concept, that's a thing that could be built into something with materialized shuffles, like potentially the materialized shuffle axle. So we actually just kind of punted on that. So we've talked about a bunch of problems and key concepts and obstacles. And to make the long story short, we did it. It took a year and a bunch of work. We made a lot of new types and serializations, 96 UDFs, like 120 PRs, internal and external, made some spatial joins. It was the last thing that was preventing Prestissimo migration. Amit was like pinging me every day, like, hey, are you done this last thing? But finally, we got it, and then we migrated everything, and then the Java code can eventually be deprecated. So that was a whirlwind tour. It wasn't very detailed. Again, ask me for any details later. I'm going to say questions, but I actually suspect we have about like 90 seconds for questions, so maybe we'll pause.